Alright, I am back. Let us get on into it. This is going to be a bit more informal than a normal lecture. We're going to write this PowerPoint together. So let's talk about const. A const, I'm throwing my microphone around, sorry. Const is for when you don't want something to change. You can convert to a constant. Const stands for constant, by the way, when you pass a variable to a function, which is super nice. So in code, you would write something like this. You would say, all right, maybe we're inside of main or something. You'd say, all right, double const pi equals 3.14 blah blah blah. And now the beauty of const is that the compiler will keep you from ever changing pi. If you were going to say like screw it, pi is now 3, the compiler would not even compile the program. This is not allowed. You have to get rid of that line. And so that's a really nice thing about const. And another nice thing is, say you are passing a variable to a function. Perhaps that variable itself was not const, but you can up convert to const as you pass it. And let me give you a better example for what that means. I guess we'll have to go to code. So here's my handy dandy code from class folder. It's in a weird place on my machine, but let us go inside of CSCI 41, and we're going to make a file called const.cpp. Some people use .cc, others use like capital C. I use .cpp. It doesn't really matter. So let's start editing this. Oh goodness. Did it make the file? How dare I? We're off to a good start. Alright, we're in the right file now. Include iostream for no good reason. And the main function. Alright. Return 0, of course. Now, double const double pi equals 3.1415926535. Okay. We have pi. We know we can't change it. Pi equals 3. This will actually give us a compiler error. And the compiler is kind of hooked into my Vim right now, so this is beautiful. It's going to say, I can't compile this because you're trying to assign pi, but it's a const. So don't do that. Thank you, compiler. We shall not do that. Something nice about const is that you can up convert. And this really comes in handy when you're using references, but let's try and not use references right now. So int, I don't know, let's just make a very simple function that returns, take x and give back x plus 1. So this will be the +1 function, super simple. Int +1, int x, and this will just return x plus 1. And so the beauty of this is, say you're doing some complicated thing. Dot, 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 dot. And you don't want to change this x. You can put const in front of it to ensure that nowhere in this complicated computation you'll change x. Okay? That's the idea. And again, you'll get that error. You can't assign x. So that's beautiful. Make sure that you can't touch it. And again, you'll see this really mattering when we talk about references. So the idea is that, sure, you can call the +1 function on pi, because it's already a const. Well, it'll change it, I guess. I don't want to talk about type conversion right now. So const double x, you can call +1 on pi, sure, but you can also call +1 on a normal double. You can call +1 like this. Obviously, when you run this program, it's not going to do anything because we're not printing, but that is beside the point. So here, z gets, we say, up converted to a const. which is nice because it didn't have to start out as a const. Your variables don't have to start out as const for you to use consts in, or for you to pass, for you to pass them to functions that expect consts. Because it's super easy for the compiler to be like, ah, yes, in this function I'm not going to touch this one thing, and that in order to do that you just use that prefix const. Right, and that's the idea. It just ensures that this variable, no matter if it was originally not const, for the inside the confines of this function, it just cannot be touched. That is const. It is nice. We will use that a lot. It also keeps things from getting copied, and we'll have to talk about that in a later lecture. Const. All right, so now references. Beautiful. So a reference is an alias, we say, for another variable. So if I had, for example, int x equals 5, I can make a reference to an int, ampersand, and let's actually put it by the int sign. Say int y equals x, and so now y is a reference to x here. Is a ref to x. And in memory, what's going to happen is we had x. It held 5. When we say y equals a reference to x, we don't make memory for y. We just rename x. We give it two names. So you can say y, you can say x, same place in memory. That's what it means to be a reference, to be an alias. Okay? That's the idea there. Make that bold, maybe. And const references are where this gets nice, because pretend for a second that you knew about vectors. Let me make a new file. That'll make this easier. Vim vectors are now references.cbp. So the idea is, if I had this function, I don't know, int blah, and it took a reference to an int, and it did some fancy stuff. If I said const int reference, then it wouldn't be allowed to change it again. So int main, it's not even going to bother with IOStream because we're not printing anything right now. Go above, please. There we go. So again, you can say something like int x equals 42. Then in here, a reference can change it, of course, because we're passing along a function. We're passing along x as p, but p is going to be a reference to x, so p is a reference to x and below. Obviously, it'll be a reference to whatever you put in. And so there's our function. Does something very simple. And sorry, it's a void function. There we go. Don't complain. So if I call this, that's what's going to happen. So blah with x. X is now 43, and you can print it out to prove that to yourself. Say, though, I did not want to do that. What I can do is make a constant version of this function, blah const, and take a const int. And again, we upconvert. Even though it was an int, x was just a normal int. Now we're going to make it a reference, and we're going to make that reference constant. So, again, we get that error. You see it. Cannot assign. Beautiful. So you can return stuff now. Like, otherwise, this function is kind of useless. Return p++, maybe, or p+1. But otherwise, you're not going to really get a whole lot out of this function because you're not going to modify p. Now, you can't modify x when it's passed, which is really nice. But another thing is, and that's kind of the topic of this class, this saves tons of memory. when you use it with bigger types. So imagine instead of this int, you had like vector of int. This would ensure, first of all, references would ensure that you're not passing along the entire vector, and constant is ensuring that you're not like changing that vector. Okay, so passing along things by reference usually is going to save a lot of memory, because deep down it's probably implemented with pointers, or most likely is definitely implemented with pointers. But inside of a function, here's what's happening. We have our main, and it had its variable x, right? And in our function that used references, it was called block const. Let me just call it for good measure. Can't change x. Assume we're on this line, line 11. And we call block const. And let me actually draw it in a different color. That's the beauty of PowerPoint. Sure, it took that x, but no, block const variables, we're going to draw them in blue, but there is no, was it called p? I can't even remember anymore. Yeah, it was called p. There is no p up here. P is x, because it's a reference. So p's down here. That's a horrible looking p, I am sorry. So if you want to talk about x, you say p up here. If you want to talk about x down here, you say x. So all the blue things are block consts things. And so that's something nice about references. You're not copying x into this function, no matter what x might be. If it's a huge array, if it's a huge vector, like that would take a lot of time to copy that memory. So it saves you from worrying about that kind of stuff. Same with pointers. Pointers do that too. References allow you to save memory by not copying between functions. Oops, I thought I was in Vim for a second. Okay, so those are references. Pointers are like references in hard mode. So pointer is just, it's a variable, it's a box in memory that holds an address of a variable with a specific type. If you keep this in mind, pointers should not trip you up that much. It's known to be like a hard thing, but it's really just another box in memory. It holds the address of something else. So here's my int x equals 42. That makes a box in memory called x that holds the number 42. And then a pointer to an int star p. You read it kind of backwards. The star means pointer. P is a pointer to an int, and we'll give it the address of x. And so p holds the address of x, whatever that might be. And so let's pretend that x lives in memory at address 100. Then p will hold the value 100. You see that? And so you can draw this, like pretend that the arrow is the value 100, and that's how you draw a pointer diagram. So that is all a pointer is, and you could do the same thing that you did with references with pointers as well. You can just put const in front of it. It's all beautiful. Let me actually copy this file and do just that. Replace that with a star. Replace that with a star. And now when we're passing along addresses, address of x, address of x. So that's fine. This first one is not correct at the moment anymore, because when I say p++, it's adding 1 to the value of p, which is an address. So this will change it to be 101, which is just pointing off into the ether, and we'll give you a segfault. So we got to use the star, right? We got to say star p plus plus. And so that'll actually correctly add 1 and not do weird things. And same with this, star p plus 1, please. And that'll get the int out of it. Okay. And again, constants make sure that you can't change things, and this is really what's happening when you use references. It's just making a pointer for you. But let's see if we can draw maybe tiny what's happening. We have main, it has x, let's pretend it's 42 instead of 5 or whatever I put there. And inside of blah, remember we're passing along not x. P is not x, it's the address of x. Alright, so P does not hold 42, it holds, I don't know, address 100. And with an arrow diagram, it'll look like that. Alright, that's the idea. Pointers are beautiful and useful, and we will use them a whole lot because we'll be taking advantage of the heap. Okay, so I've actually essentially talked about all of these things already, but let me show you them in like a one big complete package. So let's make a swap function that swaps two variables. Swaps the values of two vars. Okay. So the idea is I had value x, value y. This was 1, this was 2. At the end of this, I want this to be 2 and this to be 1. Swapping. Okay. So, all right. We'll just make a main function so that we can try this out. Int x equals 42, y equals 43, let's say, and then we'll make a swap function that swaps 42 and 43. And the first way we'll do it is by value. And you know what? We're going to have to print out x and y. X space y. Very simple. Which means we'll need IOStream using namespace std. Our friends. Okay, gotta make that function, of course. So void swap by value int x, or let's just call it int p, int q. So if you remember your handy dandy swapping algorithm, it's int temp equals p or q, either way. P equals q, q equals temp. And then voila, we swap them, right? Right? That sounded a bit ominous, and that's the point. Swap dash o swap. This is how we compile with G++. It's quite possible that you have not used this compiler before, so let's talk about that just quickly. G++ is the GNU C++ compiler. And in order to compile something, you say G++, name of program, .cpp. There might be multiple files. And then you say the standard of C++ that you want somewhere. I usually put it at the front. We're going to use the standard from 2017. They're working on 2020, but it's not ready for prime time yet. And then finally you say -o, then output file. So this is the out would be whatever the name of the final executable you want it to be. Okay, that's the idea there. So that's what we're using. So I'm about to compile it now. So I did it. Now we have a program called swap. We'll run it. Oh, that's x and y. They didn't get changed. That's because this was called by value. So call by value just copies stuff. And so it doesn't work, it doesn't touch those original values like we wanted it to. Let me draw. Yeah, black's fine. So again, from main, we had x and y. (42, 43). I should be drawing bigger, sorry. And we use swap by value. I'll just call it by value. And that had p and q. But the issue was, when we called this, we called it by value. We didn't put any star, or we didn't put any ampersands up here, down there. So it's not a star, it's not a reference, it's not a pointer. just a plain old value, and it's getting copied because it's a primitive type is what it's called. And so P got 42, Q got 43, and the thing is, well, yes, there was a temp was over here doing stuff. These got swapped, but in this function, it didn't touch the x and the y that we cared about. Okay, that's what by value means. And so by reference and by pointer allow you to touch the original memory, let's say just like that. And I am running out of space here, so it's going to put that there. I'd like to put them all right next to each other for you. And that, let's move it over if we can. Yeah. Okay, so here now we can do, again, I'll draw two mains. One for by reference and one for by pointer. Ooh, that's going to need to be in a different color. Let's draw our x's and y's to begin with. Alright, so we're going to do by reference first. And so if we want references, we got to use the ampersands, and we want to actually touch these variables, so we're not going to use const. So now we do ref instead of by value. There we go. And this is by ref. What did I do wrong? No function to call. Oh, I'm so sorry. First of all, you're probably yelling at me through the screen for doing this. It doesn't actually change anything, but I should have said x and y here. I am so sorry. Let me show you by value still not working properly, because it's really supposed to be getting copied. I'm very sorry about that. Still not working, but we really do need to swap to pass x and y. And thank goodness we're trying all of these options here, because otherwise it would have taken me a while to notice it. Alright, so that one doesn't work. Does this one work? And not to spoil anything. There we go. Yes, it does. It swapped them. Why? By ref. Oh, I did what I didn't want to do. So when we do it by reference, I'm going to put all the stuff that belongs to by ref, to swap by reference, in blue. This is what we did. P and Q are the same place as x and y. So that's why we can actually touch those values. Okay. Now let's do the last one, by pointer, or by address. So essentially what needs to change is these ampersands need to become stars. And instead of all this stuff, we need to dereference all this stuff so that we actually get the ints out and change the values inside of those memory locations. Alright, so that one works. And one last one. Let's say by adder. There we go. Alright, is it complaining still? No matching. Yes, sorry. We got to pass along the address of x and y, of course, because they are pointers. Okay, so that's our code. And I'm going to be giving you all this code, by the way. So what's happening here is, I can keep the same color now, by adder. So we have variables. They're called P and Q. They hold things, but they hold pointers. So pretend that x lived at, I don't know, my favorite address, 100. Y lived at address 108, because why not? That's what P and Q hold. And they allow us to indirectly access x and y, and so that's why we can do that swapping. So hopefully I know this is supposed to be a review, but it's all coming back to you at least, or if you've never seen it before, at least maybe hopefully it's making a little bit of sense. Okay, so that's all of those fun things. I think we are good to move on. So now let's talk about the heap. Let me check my time. All right, the heap. Let us work with the heap now. What do I want to do? So the heap is a place for storing dynamic memory. That is things that you create on the fly. So you can have a piece of memory that you make brand new for yourself. Okay. And the idea there is you can say something like int star I equals new int. And I was living, I lives on the stack. Say we're inside a main and we did this. I is a place in memory on the stack as a pointer to an int. But where we made that integer was on the heap, and I points to that place. And the heap is beautiful, all shiny and brand new. We just got that int made for us. And then once we're done with it, we can say delete. Delete I. All right, and that will get rid of that int on the heap, and we should never use the pointer anymore. All right, that is, doesn't look like I still. There we go. So that is the heap in a nutshell. Let's give a more in-depth example with arrays. So an array is like a vector, but worse. An array is just a bunch of memory right next to it itself. How do I want to say this? Array is just a bunch of memory, a bunch of contiguous memory. That is actually understandable. So if I say I want an array of something, I can do this. I can say I want an array of ints called ARR with 5 things. This will make an array on the stack. 2, 3, 4, 5. Holding random things at the beginning, of course. So that's nice. An array is just a place that I can hold a bunch of ints at the same time. Well, where this gets cool is you can maybe you don't know how many things you need at the very beginning. Like you're waiting for the user to tell you, oh, I'm about to enter 7 things, get ready for that. Or I'm about to enter in another call to that program, another run of that program. Oh, I'm going to enter 42 things now. Be ready for that. And the way you do that with arrays is to make them dynamically on the heap. So say you know how many you need, like int count. And you get that from the user, cin count. Then you can make an array on the heap by saying something like this, int star ARR equals new int like this with count. And so what that'll do is you had your ARR here on the stack, and it points to a place on the heap now that is not just one int, it's an array of them, as many as we asked for. And again, because it's on the heap, it's all shiny and brand new. So that's beautiful. And once we're done with it, of course, we can say delete. But because it's an array that we made, you need to tell C++, oh, it wasn't just one int. Don't delete just the first int. It was really an array. So you got to use delete bracket bracket ARR, and then that'll make it go away once we're done using it. And so yeah, the heap is beautiful, especially for arrays like this. I encourage you to try this out. And then finally, or almost finally, vectors is the following. So a vector, hopefully you're familiar with, it's essentially a dynamic array. But let us talk about that at a bit more of a high level. It's like an array, but you can add to it as much as you want. It can change. It's beautiful because it can change. And so if I had a vector, I could make it store things like this. And please try this out. I can say I want a vector of ints and I'll call it v, and we can just start it out being empty. So v is a vector. It lives on the stack at the moment, but we'll get into where it really lives later. And right now it's empty. Of course you have to include vector if you want to use vectors. And so if you've never seen this syntax before, it's saying that v is a vector and it holds ints. Okay, that's what that is saying. And then we can start adding stuff to v. You can say v.pushback 42. And so now at this point, v is looking like this. And then if I say v.pushback one more time, we'll say now v looks like this. No, sorry. What am I doing? 42, then 43. It puts it at the end. And if I ever want to see out something, an index, the safest way, you can do like an array, you can use the brackets, v of I or whatever. But I encourage you to always use .at, whatever index, so v at 0, I guess. And this goes to the index of v at 0, and it'll print out 42 for us. Okay, so that's a vector. It's an array that can change, and I want you to get used to going to the documentation. So let's see, c++.com, reference, containers, vector. Here we are, vector. Here's all the stuff you can do. We just talked about pushback. You can also pop back. You can get stuff out of the array. Let me make this a bit bigger for you to see maybe. You can erase from the vector. And we'll talk about all these things as they come up, as we need them. You can start it out with a specific size if you wanted to. That will get into the constructor of the vector. You can look into that. But yeah, please look into the documentation for vectors if that's something that isn't too familiar with you anymore. And so there's that. And then finally, exceptions. So exceptions are like a way to signal that something bad happened, but that bad thing can be recovered from. That's different from like calling the exit function in C standard library and being like, nope, just stop the program. I give up. So an exception looks like this, and so it can be caught, is how we say it. And when an exception gets raised or thrown, you can catch it. So thrown exceptions can be caught. That is the metaphor that somebody came up with, and we've all just been rolling with it throughout the years. Okay, so that's what that means. And you can handle them, and the program can continue after you've handled them. So my simple example is you're a waiter and somebody is ordering pizza and they do something silly like order pineapple on that pizza, and obviously we're going to throw an exception and give them something normal. All right, so let's write a program like that. Vim exceptions.cpp. And we'll just do a simple one. We'll probably use string as well. Int main, return 0. So let's ask the user, what do you want on your pizza? And give them space to enter that. Ask for their response, get it. Obviously, you could probably do this fancier by getting a line at a time. We're just going to assume that everything only is one word long. But here we're getting a response from the user, and we'll say, all right, we'll check. If response is equal to pineapple, then something horrible happened. And normally, you'd say, all right, stop the program. I cannot recover from this error. something like that. And in order to use this, you'll have to include cstdlib for that exit function. But this is what you would normally do in the face of an error. Exceptions -o exceptions. Something like that, and instead of continuing the program, of course. And so this, at the moment, will never get printed out. So, instead of this, I'm going to comment it out just so that you can like see it. Let's just use this kind of comment. Dun, dun, dun. One more. There. Instead of doing that, let us do the following. Maybe, how do we want to do this? If response equals pineapple, we will throw an exception. We'll throw the pineapple string as an exception. And so that's that. So this is how this works. Exceptions happen. They occur when they're thrown. That's the lingo. And you can catch them to recover from such an exception. So right now, still, I'm going to throw this exception, but the program's going to stop early because, because we have not handled the exception. Okay, it's going to say weird things. Abort. We have not handled that exception, but we can handle it. You can say, try to do all this. It's quite possible that you will fail, but I know how to recover when you do. So it's called a try-catch block. All right. This is how this works. So now, if we ever get inside of here, then a string was thrown to us. And oops, I'm gonna do this right now. I have to make sure it's a string, otherwise it's a weird const char star. We don't want that. So if we got inside this catch block, a string was thrown, and it's possible for us to, and the reason we have this catch block is because we know how to fix it. We can fix the problem. Okay? So we can say something like, all right, because we got here, fixing the pineapple. Assuming the string that got thrown to us was pineapple. We can say, all right, we're fixing the pineapple. And we can do something like change it. We can say resp equals pepperoni. Hopefully that's how you spell pepperoni. Okay, so that's the idea. That's what a try-catch block gives to us, and it will allow our program to continue. So let's see out response back to ourselves, and so let's run this program now. You can say something silly or something normal like cheese, and it'll just continue. You'll never hit the catch block because you're never going to throw an exception. Only if you have pineapple, we're going to throw that string exception, and we'll say fixing the pineapple, and I forgot a new line, and then the program continued, and we changed it to pepperoni. Okay? That's the idea. Obviously, there is a lot more to exceptions than what I'm showing right here, but this should be enough to get us started. So this try catch block is what is the key. Try to do the following. And if an exception happens, and it's one of the types that we care about, then we'll move on. You can have multiple catch statements. You can say catch, I don't know, maybe you're going to throw an int in this case. And it's customary to catch by reference. Handle an int. And that's the idea. So hopefully that makes a little bit of sense. And with that, I think we are good in terms of review. So thank you for watching if you chose to watch this. That is all I want to say. Remember to try and then catch. And yeah, so that's the end of the review. Let me pause this, and then we'll see you back in the main lecture. Oh, sorry, I forgot to give you a prize for getting through the review, this beautiful slide. Okay, now I'll see you back in the main lecture.